Just to finish off, there are a couple of warnings that go along with partial derivatives that you need to be a little bit careful about, and I should say something about those now. The first warning is not super serious, and that's about notation. When we did partial derivatives, we used to use notation like this. We just used to write like f prime for the derivative of a function, or f bullet if we had the derivative of a function. The problem with notation like that is that it no longer tells us which derivative we're doing. It doesn't tell us whether we're doing the x derivative, the y derivative, any of that. And so it makes it difficult to keep track of what's going on. So we need to use some notation that remembers which variable we're taking the derivative with respect to. So the dx notation is okay, and the del f del x notation is okay. But that's important to remember that we're changing. A second warning, which is a little bit more serious, is that it's very important that we remember what we're keeping constant and what we're not. This is not going to be as big a deal in this class because we're usually going to try and keep a little bit of separation between different variable names. But out in the real world, you might encounter multiple situations where you have two different ways that you could think about the same different situation by changing how we think of what the inputs to a process are. And the notation for partial derivatives does not help us remember what we're supposed to be doing. Now, this sounds like vague and weird, so let me give an example, which is not something you should know, but it has to do with electricity, in particular, something called Ohm's law. There are three quantities that are interrelated to each other called EI and R. They're for voltage, current, and resistance, and they're related to each other by Ohm's law. Voltage is equal to current times resistance. And there's an output variable that we can think of that depends on those called power. Power depends on voltage and current. It's the product, I times E. Or if we like, we could use Ohm's law, and we could say that power is also equal to I squared times R. Both of those, this says that power is some function of current and voltage. This one over here says that power is some other function that depends on current and resistance. When we take partial derivatives, we get two different answers for the partial derivative. If I calculate the partial derivative with respect to I on the left-hand side, I get just the voltage. Whereas if I calculate the derivative of power with respect to current on the right-hand side, I get twice the voltage. And these look like they're mutually incompatible answers. The point of this story is supposed to be this one on the left measures what happens when we change power, or what happens to the change in power when we change current. But what we do is we keep the voltage constant. That's the important part, is the formula on the left-hand side is measuring change when we keep the voltage constant, whereas over here, this one is keeping the resistance constant, which is mutually exclusive from the situation on the other side. So even though these are two functions, they measure the same thing, and they both depend on current as their input, it's important to remember that the other variables we're using are equally important to keep track of when we're doing partial derivatives. So that's more a warning for when you actually get out there and apply these things, but it is the kind of thing that can seriously burn you.